For how many positive integers k does the ordinary decimal representation of the integer k factorial end in exactly 99 zeros? Okay, so this is, a lot of people will have seen a similar problem to this, and it basically comes down to understanding that for a number written in base 10, if it ends in a 0, that means the prime factorization has a 2 and a 5 in it. If it ends in 2 zeros, it has 2 2s and 2 5s. There might be more 2s and there might be more 5s, but for every 0, there will be a pair of a 2 and a 5 in the prime factorization. So, if I want to find out for how many integers does the ordinary decimal representation of the integer k factorial end in 99 zeros? So, as I, if I write down k, 1, 2, 3, 4, 5, 6, 7, and so on, and here k factorial, 1, 2, 6, 24, 120, 720, and so on. If I'm looking at the prime factorization of these numbers and counting pairs of 2s and 5s, then because anytime I add a 2 or a 5, it's because I'm increasing k. So as I go from 2 to 3, 3 gets added as a prime factor. As I go from 3 to 4, I multiply by 4, so I've actually multiplied by 2 twice, so I get 2 factors of 2. Then I multiply by 5, that's multiplied by a single factor of 5. Here I'm multiplying by a factor of 3 and a factor of 2, and then 7, and so on. New factors of 5 get added more slowly than new factors of 2, so I really only care about the factors of 5. Okay, so in order for there to be 99 factors of 5, well, I need let me think. What do I want to count here exactly? I want to take k and divide by 5 and round down. This is the number of factors of 5 less than or equal to k. But I have to remember that when I add a 25, I get 2 factors of 5. So, or when I increase k beyond a multiple of 25, I get 2 factors of 5. So I also have to take 2 times k over 25 floor plus 3 times k over 125, take the floor, plus 4 k over, is it 625, is 5 to the 4, and so on. And I want the number of solutions for k such that this is equal to 99. Okay, so let's ask ourselves what a reasonable range of k is going to be. K is certainly going to be less than 500 to satisfy this, right? K divided by 5 is 100, so we're already too large. What happens if I let k equal 100? Then k over 5 is 20. Plus 2 times k divided by 25 is 4. 2 times 4, and the rest is 0, so that's only 28. Okay. I'm just trying to narrow in on what a reasonable value of k is. What about k equals 400? K over 5 is 80. K over 25, 16. k over 125. 125 times 3 is 375. So 400 over 125 floor is 3. What is this equal to? 80 plus 32 plus 9. That's too big. So it's again going to be less than, 400. Is there a way that we can figure this out by just by not actually solving for k, but understanding can the answer even, are there any values of k which make this true? Because it's possible when k passes a multiple of 5, we might jump from 98 straight up to 100 because the next multiple of 5 happened to be a multiple of 25 also. I feel like I want to just kind of go through the guesses here to try and figure out what k could be. So k is 100. I've got 28. K equals 200 is going to give me that times 2 plus, there's a 125 in there, so times 3. So k equals 100. This gives me 28 times 2 plus 3, which is what, 56 plus 3, which is 59. What if I go up and look at the powers of 5? Well, I mean, no, 625 is already too high. 125 times 2 is 250. Okay, so 250 over 5 plus 2 times 250 over 25 plus 3 times 250 over 125. This is equal to 50 plus 25 over 250 over 25, 10 times 2, 20 plus 6, 76. And that's at a power of 5. So 76 will increase every time k goes over a multiple of 5. Two, 3, 4, and 82. And then 83, 84, 85, 86, 88. 90, 91, 92, 93, 95, 96, 97, 98, 99, 101. Okay, so I think the answer is going to be 5. But so this is for 250. 250. 1, 2, 3, 4, 5. So that's 275. 1, 2, 3, 4, 5. 300. 2, 3, 4, 5. 350 and 375. Oh, so it won't go to 101, it'll go to 102, I think. So 375. So that means this should be 370. Let's test my formula with k equal with numbers around 370. So 370 over 5 floor plus 2 times 370 over 25 floor plus 3 times 370 over 125 floor. That's equal to 370 divided by 5. Well, 350 over 5 is 70. 74 plus 2 times, this is going to be 14, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 13, 14. And this will be, is this 2? Yeah. 74 plus, did I miscount something? That's bigger than 99. For 250, right, 76. Every time I go above a multiple of, but 250, the next multiple of 125 is not till 375. So 1, 2, 3, 4, 5 times 5. Oh my goodness. This should be 325, which makes this 350, which makes this 345. Okay, so for k, 345. 345 over 5 plus 345 over 25 times 2. Well, round down then times 2 plus 3 times 345 over 125. Round down. 345 over 5. 350 over 5 is 70, so this is 69. 300 over 25 is 12 plus 1, 13. And this is 2. 69 plus 26 plus 6, 69 plus 32. That's too big. This is 101. Oh, gosh. So I've counted something else incorrectly. Eight. Oh, man. I wrote up my table incorrectly. 89, 90, 91, 92, 94, 95, 96, 97, 98, 100. Okay, so I think the answer is 0, in fact. We could show that, right? This will be the number for 350. Did I try 350? No. 350 and 340. But I did do 345, didn't I? And it's too big. Why am... Oh, come on. What is wrong with me? $350 divided by 5 is 70. So this is 69. 300 divided by 25. 12 plus 1, 13. And this is 2. $69 plus 26 plus 6. 69 plus 32. That's 101. Why is does the pattern break? Did I do, is this one incorrect? 250? $250 divided by 5 is 50. 250 divided by 25 is 10. 250 over 125 is 2. 50 plus 20 plus 6, 76. Well, I'll call it Z, the number of zeros. 76. Oh my goodness, no. No, I shouldn't be multiplying these numbers by 2 and 3. I'm already double counting. The whole purpose of adding... Oh, man. The whole purpose of adding the other factors is to account for that double counting already. My whole initial formula was incorrect. Okay, let's go back to... so these numbers are higher than they should be. 400 was higher, but not super high. 400 over 5 plus 400 over 25 plus 400 over 125. Floor all of these. 80 plus 420 divided by 25 is 16. And this is 3. 96 plus 3, which is 99. Okay, so the answer is going to be 5. Oh my goodness. Wait. Nope. Yeah, 125 times 5. No, 125 plus 125 is 250. 250 plus 125 is 375. Yeah, so 400 is nowhere near a cube. Okay, and I can even find the number, so it's going to be 400 up to 404. These are the values of k that work. 400 to 404. So the total number of integers for where this works is 5. Oh my gosh. You think you've seen a problem enough times, you'd be able to solve it without making such a blunder mistake. This formula is wrong because I don't need these 2s, 3s, 4s, and so on. I'm already, that's why I'm adding these new terms here anyway, is I want to double count multiples of 25 and triple count multiples of 125. But I'm already single counting every multiple of 5 and double counting multiples of 20. Anyway, yeah, that was very silly of me. But there we go. I get that the answer is 5. I'm not going to go back and look for more mistakes on this one. I might still have some. Maybe I made arithmetic mistakes even in this corrected version. But I'll let you know what the right answer is if it's not 5. Thanks for watching.